Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome back to the lecture. We are looking at mechanical testing. Primarily we are looking at tensile behavior, and in the last lecture we discussed about the effect of strain rate and temperature and constitutive relations in terms of stress and strain, how the material behave and so on. So to complete that discussion, I just want to show a few more examples. What you are seeing here now is a plot of stress versus true strain plot, and then you have also see that d epsilon t by d d sigma t by d epsilon t, that is what hardening rate is superimposed on this true stress true strain curve. So what you are seeing, this is for typically an FCC metals, and also it shows the temperature effect, the low temperature and then high temperature, and then how the FCC metal responds to the deformation at these conditions. So what is that we are seeing? So okay, before we even we look at the description of this, let us look at this. This is a similar plot for BCC metals, and again you are seeing the stress strain response at two different temperatures similar to this. So the primary purpose of this slide is to show the difference, the kind of difference the two class of material exhibit. So what are the primary difference? The primary difference is, as we have already seen, that FCC metals do not show any significant influence of yield stress. On the other hand, BCC metals exhibit significant influence of temperature. Okay, so that is the first observation. Schematic of true stress, true strain curves for a typical FCC metal and typical BCC transition metal. Plots of d sigma t by d epsilon t, the work hardening rates of the respective metal classes are shown in the figure. So for a FCC metal, sigma y, that is yield stress, is relatively insensitive to temperature. So we are, it's almost a similar behavior from here. But the work hardening rate increases with increasing temperature. Okay, so the work hardening rate, if you look at it, increases with the decreasing temperature. So this is what the work hardening rate is higher here, but is for the low temperature, and then so you know the point of, you can see that inflection. What is the meaning of this point of inflection, that you have already seen, right? So but now we have to compare this epsilon neck, that is point of instability, at these two junctures. It's quite interesting, right? What is that? Since the tensile geometrical instability occurs when d epsilon t by d sigma t by d epsilon t is equal to t, that means sigma t, these features lead to a lesser necking strain with increasing temperature for FCC metal. Very important observation. So we are looking at two point of inflection, that is point of instability, and the epsilon neck is lesser, okay, with the increasing temperature for FCC metals. This is quite interesting observation, right? Okay, we can now relate this point with other fundamental quantities like stacking fault energy, strain hardening exponent, strain rate sensitivity at high temperature. And if you put all of them together, you will again get some more clarity on this. If you look at the BCC metals, the yield stress is highly temperature sensitive. So you see that there is a huge gap between the yield point. Okay, so highly temperature sensitive, but the work hardening rate is not similar. Unlike the FCC metals, the work hardening rate does not get influenced by the temperature. So what does that mean? Thus, for these metals, the tensile necking strain increases with increasing temperatures. Okay, so it is just opposite to what we have seen for FCC metals. The neck strain, that is point of instability, increases with increasing temperature. So these are all very important observations, and which will be useful to interpret the high temperature behavior of these class of materials, at least. Now, again, we will look at some combined plot of strain rate and temperature effect. And this plot is not quite commonly reported in most of the text, but it is very interesting and important plot. What is that? It is again relative stress versus strain plot. And again, you have a stress strain curve, slow strain rate as well as high strain rate. So slow and impact. Okay. And then at 3 different temperatures. This is room temperature data, this is intermediate temperature data, this is a high temperature data. So what is that we are seeing here? It is the mark here is the stress and strain at 1 demarcates the stress strain relation of material at room temperature, the maximum stress, okay, at strain 1. So just keep a reference for this, and then we look at it. So what is that we are seeing now? So we generally know that as the temperature goes up, the strength comes down. This is what you see in most of the stress strain plots, right? The level of stress strain curves comes down as the temperature goes up. But something can be compensated, but the strain rate, as increasing strain rate, it also increases the stress strain curve. Okay, so this is an opposite effect. The strain rate has got an opposite effect. So it's a kind of, we can make a comment like the decrease in the stress strain behavior can be compensated by the increase in the strain rate. Okay, that kind of analogy we can bring in. But what you see here is at room temperature, the difference in the slow and impact load is quite different from other temperatures. You see that the difference in the normal strain rate and the high strain rate deformation, the difference is very high as compared to the room temperature. You can see there, and it is much more higher in the high temperature. So at the difference between these two, slow and impact loading at high temperature is the highest. Okay, so this is how we should compare it. And now we'll see the lowering of the stress strain curve at elevated temperatures may be compensated by increasing strain rate. Although this compensation occurs only while the high strain rate persists. It may still be important for those applications where the required life of the part can be short. Okay, so this is a specific applications where we can still, this will be of some use. So this can be a solution. If plastic flow occurs more rapidly than the diffusion can eliminate its effects, the metal can then be used under rapid loading at high stress levels, even at high temperatures. So what are the problems at high temperatures? High temperature means your diffusion rate will be very high, and whatever the the recovery process, grain growth effect, all this will influence the microstructure, and which in turn reflects in the stress strain behavior. Okay. On the other hand, the high strain rate will compensate that, but then what is important here is if the plastic flow occurs more rapidly than diffusion, it has the rate of plastic flow should be much more than the diffusion. Then those effects can be eliminated. I mean, the microstructural change, whatever happens because of the high temperature, can be compensated provided the plastic flow rate is much more than the diffusion. Okay, that's the idea. Although the static stress strain curve may drop very rapidly with increasing temperature, the percentage increase in strength due to impact loading is much greater at elevated temperature than at low temperatures. So that is what's shown here. Okay, the percentage increase in strength due to impact, okay, is much greater at elevated temperature than at the low temperature. So this is one nice information which predicts in one plot the effect of strain rate and temperatures in a polycrystalline material. The strength of metal at elevated temperature is greater under impact strain rate as compared to the low strain rates. And I'm just showing another very interesting plot. What is this plot shows? It is UTS, the ratio of UTS impact to UTS slow, high strain rate to slow strain rate ratio, versus fraction of melting point, that is temperature in Kelvin divided by temperature, that is melting point in Kelvin. Usually this fraction is called homologous temperature. We will see it in the high temperature behavior. We will use the term homologous temperature. Normally this is called homologous temperature. Okay. So it shows very interesting trend, like how the strain rate and the temperature, influences the deformation behavior. What is that we are seeing here? So the most of the material, at least metals here, we are referring to metals, it starts, responding to this high strain rate approximately, suddenly it just goes up approximately in the 40 to 50% of the melting point, that is 0.4 to 0.5 TM. Okay, that is, this is the range. The response is quite significantly rising. Okay, most of it. So what is that microstructural change that will occur under this temperature range, that is 40 to 50% of the melting? So most of the recrystallization, recovery, all this process rapidly start taking place at this temperature. So it will have, that's why it has also started responding significantly in this range. Okay, but here there is a division, a range of temperature range is quite high. So that means you have materials, for example, light materials like aluminum, magnesium. Okay, they will all which will respond to the high temperature very slowly, which will fall into this region, the right hand side of the dashed line. Okay, but the materials which exhibit a sudden change in the structural features, okay, they will fall at low, sudden change in the microstructure at relatively low temperature as compared to these light elements, they will fall into this category. Okay, at very low temperature, the sudden change is there in the microstructure, so they will all fall into this category. Okay, so you can compare that iron or steel or something like that, just to give an example, but this is a very general diagram. But the extreme right, this category, all the light elements, aluminum, magnesium, and so on. So basically, the insensitive, no, the temperature sensitive, temperature insensitive. That's what we have seen in the previous slides. And also how it responds to the strain rate. Okay, so like I said, we can put all these parameters together, like stacking fault energy and strain hardening exponent, strain rate sensitivity. All these parameters we can put together and then compare how these things are going to help in understanding this. So we have spent quite a bit of time on this interpretation of this stress strain behavior, especially during tensile test. We will now move on to some other material classification, mostly polymers to start with. We know that polymers are all made up of covalent chain molecules. So they are all covalent bond in the intercarbon link, but they are also bonded by secondary bonding between the two chains. Okay, that and all we have already seen in the introduction. But then this configuration, chain configuration, has got something to do with the strength. How they are related? So suppose if you classify this kind of bonding nature as a linear, and these are all called branched chain molecules, and this is cross-linked chains and configuration, and then finally a network. So interestingly, you can see this the direction of increasing strength in polymeric materials like this. So from linear to network, the strength increases. Okay. So how do we understand this in a simple tensile test? And before even looking at that, we need to look at little more some properties about these polymers. Thermoplastics versus thermoset polymers. What are thermoplastics? They are all characterized by little cross-linking. They are ductile. They soften while heating. For example, polyethylene, polypropylene, polycarbonate, and polystyrene. And what are thermosets? They are all large cross-linking molecules. They are the primary bonding, and 10 to 50% of them are. They are hard and brittle. They do not soften while heating. Examples is vulcanized rubber, epoxies, polyester resin, phenolic resin. Okay, so these are all the examples for thermosets and thermoplastics. But if you look at their general behavior versus temperature versus molecular weight, because we are talking about the chain configuration, obviously the molecular weight has a significant role to play. So as the temperature increases, it forms a mobile liquid in this region, and then if you look at the increasing polymeric molecular weight, then you have the crystalline solid and partially crystalline solid, which is there just below the Tg. And below Tg and Tm, that is very interesting, and you have very tough plastic, higher molecular weight, and this region tough plastic. And then above this Tm, then you have a rubber and complete viscous liquid, and this is mobile liquid. So this plot gives, depending upon the molecular weight and the temperature, the polymeric behavior is decided. Okay. So then it will give us already, it already gives us an idea how this is going to respond in deformation to some extent. So that's why this slide. So the type of tensile deformation which we are going to see is in line with the previous classification. This is elastic, heterogeneous plastic, and then homogeneous plastic, like 5. So this is the typical, we are talking about this type of behavior: elastic, heterogeneous plastic, and then homogeneous plastic. Okay, so we are talking about only this, and the other two are already seen. Linear we have already seen, and this one is we are going to see now. So this is a stress strain plot for typical polymers, and there are three types we are showing. One is a brittle polymer, and is a plastic polymer, and an elastomer. Okay. So the soft rubber is also considered as an elastomer here. So this curve is almost similar to this. So brittle means we can simply relate that with the networking of chains, and we have seen that characteristics in the previous slide. And then you have the plastic with significant ductility and strengthening. So this is plastic, and significant strengthening means it can go up again after coming down. That's why it's plastic and significant ductility and then strengthening. That is how this is described. And this type of curve is described as elastic but nonlinear to large strain. Okay, it is called something called hyperelasticity, also known as rubber elasticity. So there is no load drop in the rubber elasticity, which something you can witness, which is quite different from the other stress strain curve we have seen. There is no load drop in the hyperelasticity or elastomer deformation. It just increases and it keep on increasing till fracture. Okay, but on the other hand, this polymer shows a load drop and then ductile exhibit significant ductile behavior and then strengthen. Okay. Okay, so strains are possible up to 1000 or more than 1000%. So you can see that kind of deformation possible in this kind of materials. So what is responsible for this kind of behavior? So we will just see one by one. We will first look at the brittle failure of this polymer. So as I just mentioned, to start with, they are all networked polymeric chain, and they are all aligned and cross-linked to start with. So what happens as the load goes up? That is the idea. So it is initial, and this is a near failure. So nothing happens. So literally no movement. So it just breaks. It's all intact. Nothing happens to this network. Very strong network. On the other hand, if you start with this semi-crystalline polymer, which exhibits elastic, heterogeneous plastic, and homogeneous plastic type 5 stress strain behavior. To start with, they are all semi-crystalline in nature. So you see that crystalline region, and then in between there are some semi-crystalline region or amorphous regions. These chains are all randomly oriented here. As the strain increases, the schematic clearly shows that elongation. So this point is before the yield point, still in the elastic. So it's exactly on the onset of necking. So crystalline regions align. So basically, the alignment of this chains takes the load up to this point. Then after the necking, the load drops significantly. That is because of the crystalline region start to slide with each other. So you can see that it all broken into small segment and then start sliding with each other. So that is the load drop is because of that. And then finally it hardens. Why it hardens? Because it is trying to stretch completely. It becomes a fibrillar structure. It is no longer a crystalline and amorphous combination. It becomes a single line, almost fibrillar structure. Okay, they are all getting stretched, all this molecular chain. So this clearly brings all the mechanisms of deformation in the brittle and plastic polymers as compared to metals and other materials, what we have seen. It is quite different from what we have seen before. So here also we talk about necking. So if you look at the necking, what happens in this region, you see that it is a complete molecular arrangement during neck propagation of glassy polymer. So necking here means that all the non-crystalline region becomes straight alignment, so basically pulling the strain straight into one direction, that is stress direction. Extensive alignment takes place in the neck as this strong region propagates along the gauge length and converts the less deformed and aligned material into molecularly oriented structure. So it is something similar to a Luder band, we were talking about. Here also it is it propagates, the necking propagates throughout this, and then finally it stretches. So that's about this polymer, very interesting. And what kind of deformation process people engage these polymers? So drawing is one of the primary process. It's also called monofilament fish line. Stretches the polymer prior to use. Align chains in stretching direction. That is one operation. Why do we do this? Because this operation increases the elastic modulus in the stretching direction, increases the tensile strength in the stretching direction, and obviously it will reduce the ductility. So this kind of configuration just we have seen at the point of fracture. So this operation, it's called drawing operations. Just it is connected to the deformation. We can also anneal them like metals. This materials can also be subjected to annealing, and then it will produce. It results in this operation, annealing operation, will result in decreasing the alignment, and it also reverses the effects of drawing. So it will get back to some of the original configuration. Yeah, this can be simply compared with the cold working of metals. If you talk about brittle and plastic behavior, now we'll talk about the elastomers. So elastomers, to start with, they are all amorphous chains entangled in it could be completely kinked and cross-linked chain molecules. That is the starting point. And as the deformation proceeds, it is going to absorb quite a bit of a strain up to this point, which is still reversible. Then at the point of fracture, then again the chain alignment takes place. Chains are straight and then still cross-linked. Okay. So the significant amount of strain is absorbed in the process of basically aligning this kinked and cross-linked chains, right? So that is what it is shown there. So compared to other polymers, they are showing brittle response, aligned and cross-linked network polymer, and plastic response is mostly from the semi-crystalline polymers. So what is the temperature and strain rate effect here? So here also you can see that the low temperature making them highly brittle, and then high temperature, relatively high temperatures make them more ductile, similar to metallic materials. Decreasing temperature increases E, tensile strength, and decreases elongation, and increasing strain rate, same effects as decreasing temperature. Okay, so that's about a brief presentation of polymeric tensile tests or deformation, tensile deformation. Now we will focus on the torsion test.